Good afternoon and welcome to today's webcast titled Understanding Nutrient Issues Affecting Ohio's Inland Lakes. This webcast is sponsored by EPA's Watershed Academy and EPA's Office of Wetlands, Oceans, and Watersheds, also known as OWOW. I am Ann Weinberg with EPA's Watershed Academy, and I will be co-moderating today's webcast along with Kevin Kratt with Tetra Tech. Thank you all for joining us today. We'll start by going over a few housekeeping items. First, I'd like to briefly summarize some of the features of today's webcast. We hope you all will have a lot of questions. Please type your questions in the questions box on your control panel and click send. If your control panel is not showing, simply click on the small orange box with the white arrow to expand it. If you have any problems viewing the broadcast, just let us know in the questions box, and we will post an answer in that same box. This webcast will be archived for later viewing on EPA's Watershed Academy webcast page at www.epa.gov/Watershed Academy. Also, a PDF copy of the slides are also posted on the Watershed Academy website. And participants are eligible to receive a certificate for their attendance at the end of the webcast. Directions for obtaining this certificate will be presented at the conclusion of the presentations. The materials in this webcast have been reviewed by U.S. EPA staff for technical accuracy. However, the views of the speakers and the speakers' organizations are their own and do not necessarily reflect those of U.S. EPA. Mention of commercial enterprises, products, or publications does not mean that U.S. EPA endorses them. So now that we have completed the discussion of some of the introductory items, let's kick off today's webcast. Let me introduce our highly esteemed speakers. Today we will hear from three folks. Rick Wilson, who is with the Ohio Environmental Protection Agency's Office of Water. He is an environmental science specialist in the Division of Surface Water. We'll also hear from Dr. Harry Gibbons, who is a scientist with Tetra Tech. He has years of experience leading management and restoration programs for over 250 lakes and reservoirs and 35 stream and river systems. Harry is also a past president of the North American Lake Management Society. Shannon Bradabo will be our third speaker, and she is also with Tetra Tech as an environmental engineer. She is currently the North American Lake Management Society Region 10 Director. For their full bios, please see the webcast flyer on the Watershed Academy website. And I want to thank you to all of our speakers for joining us today. We're certainly being eclectic here. We've got Harry on the West Coast in Seattle, Shannon in Spokane, Rick Wilson, Ohio, and Kevin Kratt in Ohio, and us here in Washington. So we're testing the technology or using it to the fullest. As a final note, before we kick off the presentations, we will try to answer as many questions as possible throughout the webcast. We will pose questions to each speaker after their presentation, and if time permits, we'll take any remaining questions at the end. However, due to the high number of participants and also a large number of slides, not all questions will be answered, so please do contact the speakers after the webcast. The speakers' contact information is on one of our final slides. And with that, we'll begin our presentation. I will now turn it over to Rick Wilson to provide an overview of the webcast and to discuss Ohio's Inland Lake program. The floor is yours, Rick. Take it away.
Good afternoon or good morning, depending on where you're at. So I was asked to provide an intro to this webinar to provide some background on Ohio EPA's lake monitoring program. As you can see on the overview, we're going to talk about a brief history of and status of Ohio EPA's inland lake monitoring, lessons learned about Grand Lake, St. Mary, Buckeye Lake, and a couple other lakes, Kaiser and Alma, that Tetra Tech has helped us with. Going to spend a little bit of time at the end of my presentation on the challenges moving forward, including see the fine print, how to understand and build basic environmental awareness and lake management through basic limnology and through building stakeholder support. after I'm done, Tetra Tech is going to jump into information that I think is key to Ohio, but I think will have applicability across the United States and even in the world. So let's move on, and I'll give you that background. So in Ohio, this is a screenshot of Ohio's watersheds. We have more than 58,000 stream miles of streams. We have 446 public lakes, and those are lakes that are greater than 5 acres. So that you might consider that kind of what our universe is here. Wetlands, we have 940 plus thousand acres of wetlands remaining in Ohio, and that's down 90% from pre-settlement issues. The reason I bring that up is you might hear more about buffers or wetlands later on in the lake management strategy part of the presentation. So Ohio EPA's Division of Surface Waters Ecological Assessment Program is nationally recognized for top-notch hard discipline work on streams. We developed bioassessment methodologies and associated criteria that have been used to monitor and protect Ohio streams for almost 40 years. And so we have folks every year assigned to various watersheds around the state to do that type of work. It's about a 20-year rotation on watersheds on that, so it gives you an idea of the type of resources to get complete coverage, and then we can jump into lakes. So, but when we try to determine use attainment in lakes, bioassessments, which is what we do in rivers, doesn't necessarily cut it. So that's where you enter the nitrate issues, phytoplankton issues, and algal toxins. As we know, nutrient loading is the general driver for harmful algal bloom issues. So a different set of information is needed to understand, different information is needed to understand and develop management strategies. For example, in streams we conduct low flow monitoring for bioassessments and chemistry oftentimes, but for lakes, monitoring tributaries during high flow loading events to downstream is more appropriate. Historically, our monitoring has not got robust data during high runoff events. So there's been a shifted approach in recent years given the issues at Ohio's various inland lakes and other lakes around the nation, obviously. A lot of our issues, you'll see here, deal with aging impounded reservoirs. So more information on background of lakes in Ohio. We have 50,000, according to the National Land Cover Database, more than 50,000 lakes. Those are lakes of all sizes, including farm ponds, etc. We have 43,000 lakes that are smaller than 5 acres. We have 650 lakes that are greater than 25 acres, and that's both public and private lakes, and 80 lakes that are greater than 250 acres. And you could consider those would almost all be public lakes. We have 108 natural lakes. The majority of those are found in northeast Ohio between Lake Erie and the western edge of the Allegheny Mountains. The remaining lakes are mostly man-made in Ohio. Dammed impoundments at 63%, upground reservoirs, and dugouts. Because the vast majority of our lakes are artificial, Ohio's Department of Natural Resources manages them as put and take fisheries. So a lot of these are stocked for recreational purposes. Some of you out there might wonder about reference lakes. Currently, we don't have any designated reference lakes in Ohio because the reference condition implies least impacted, or in some cases unimpacted conditions. And in Ohio, for us, those types of lakes don't exist. So that's a challenge. Since 2008, 2008 was the year that Ohio's Inland Lake Program was resurrected. I think Section 314 funding ended around 1995. So between 95 and 2008, we monitored lakes as case-by-case basis where we needed information, but it wasn't nearly as robust of a program as we've had since 2008. In 2008, when we started sampling our lakes again, the emphasis was placed on lakes that fell within watersheds where we were doing TMDL studies. Since the reestablishment of our Inland Lakes program, we've monitored monitoring and sampling efforts have occurred on 78 of our inland lakes. So with 5 crews, we have Northeast Ohio, Northwest, Southwest, Southeast, and Central Ohio crews that do that sampling. In those 8 years, or 9 years, we've done 78 lakes. And then on top of that, our Northeast and Northwest district offices also do Lake Erie monitoring. Public drinking water supply lakes and reservoirs. In our 2016 integrated report, we have 16 public drinking water supply watersheds that are listed as impaired due to algae. We have 12 inland lakes on the Division of Drinking and Groundwater watch list for algae. We have 5 public drinking water supply watersheds impaired due to nitrate, and 27 watersheds on the Division of Drinking and Groundwater's watch list for nitrate. So more on the drinking water aspects of this. With the discovery of algotoxins in source water at Salina and in Akron and other water systems during our National Lakes Assessment, Ohio EPA's leadership decided that the focus needed placed, rather than in TMDL watersheds, they needed placed on public water supply lakes and associated source waters. In fact, a small subset of water systems have had algal detections in finished water. So these issues highlighted the need for enhanced oversight of monitoring, treatment optimization, and source water protection and management. And so last year, Ohio EPA's Division of Drinking Groundwater's Harmful Algal Bloom section was formed. That's a new section, a new program at Ohio EPA. Their role is that they oversee the rules for our harmful algal bloom monitoring, reporting, and treatment techniques for public water systems. They also partner with the Department of Natural Resources and the Department of Health in recreational waters, primarily at recreational beaches. This is in regard to harmful algal bloom related sampling and reporting. Right now, there are almost 100 public drinking water supply watersheds where there's insufficient data available to determine their attainment status for algae. But this will change in the next reporting period, since new monitoring rules now require sampling for algae at all public water systems. Note on this map here, you see the several to many public water systems on Lake Erie. We also have crews monitoring those systems as well. Inland lake monitoring in 2016. 2016 was a big year. We like I mentioned, we shifted from TMDL watershed type lakes and moved toward inland lakes that were either on the watch list for harmful algal blooms or had recreational issues. So we monitored 29 lakes. That's 5 crews in every region of the state. 29 inland lakes were monitored in 2016. That includes 15 that were drinking water supply reservoirs or impoundments. We had 3 lakes that are both public drinking water and state recreational use. So 10 of those lakes were state parks for recreational use. And 1 private lake that had a important hit on algae. And but what's that data used for? Near term, the information goes into our integrated report for impaired, listing waters as impaired for either drinking water or recreation. Long term, which is kind of what our work with Tetra Tech has been all about, is, okay, we know there's a problem at a lake. What are we going to do about it, and how can we make the right management decisions and work with communities on implementing the appropriate fixes for long-term solutions. So lake management planning is something that is definitely in our on our radar, and we are working toward that. But it's an evolution, obviously. So Inland Lake Sampling Procedure Manual, we've had this manual since 2008. It's updated every couple years. And there's a link here if you want to see that or want to use that for your own knowledge. You can take a look at it here. In this picture are two of our lake samplers. We have our Jeff Boney, who's our new inland lake supervisor, and we also have, we can't see his face, but Jeff Lewis is our Central District Office water quality monitoring supervisor. So moving forward, in our integrated report, we've prioritized 3 lakes moving forward. These are Tappan Lake in Harrison County, Harsha Lake in Claremont County, and that's a feeder of in the Cincinnati area. We also have the Clyde and Beaver Creek Reservoir in Seneca, Ohio, Seneca County, Ohio, and that's in north central Ohio. So the basis for choosing these lakes, we reviewed a review of the inland lakes and reservoirs that were listed as impaired or were on the watch list for algae in the 2014 integrated report, and we had recent data collected at the drinking water supplies intakes that led to an impaired listing. And so waters impaired by algal toxins in Ohio were listed for the first time in 2014. In the 2016 report, more waters were listed, especially lakes and reservoirs. So we wanted to emphasize the protection of public drinking water supplies with our priority lakes moving forward. Near-term priorities for Ohio EPA, the obvious focus falls on harmful algal blooms in drinking water sources in lakes and reservoirs. Big issues for communities. They all have input and they all have a role. Many public water systems are experiencing the increased treatment costs and stigma for having algal blooms in their reservoirs, and they also have to, like I said, the treatment costs are to manage the extra carbon load and cyanotoxins at their intakes. Smaller conventional water treatment systems are having difficulty just up front even treating for these problems, and the expense for the upgrade of those systems can be pretty high. So just a visual of where things have happened with regard to our priority lakes and our work with Tetra Tech. 2009, we started in Grand Lake St. Mary's with some important issues with algae, with a harmful algal bloom and algal toxins. We worked with Tetra Tech there. Buckeye Lake in central Ohio, same issues there. Most recently, through a contract with US EPA, Tetra Tech assisted us with 2 other lakes, Lake Alamos, it's a smaller lake in southeast Ohio, and Kaiser Lake in west central Ohio. Both of those were state park lakes. Both of those had issues, or at least reports of algal blooms. The 3 priority lakes moving forward are Clyde Reservoir, Tappan Lake, which is in the Allegheny foothills in eastern Ohio, and Lake Harsha, which has experienced some substantial blooms here recently. So I was asked to give an update of Grand Lake St. Mary's. A lot of you, I hope a lot of you, if you've been involved with lakes, have heard about Grand Lake St. Mary's, which kind of became a national issue in 2009 on Father's Day. We had have a lake that's the largest inland lake in Ohio at 13,500 acres. Watershed size is pretty small, 59,000 acres or so. That major bloom happened in 2009, and on Father's Day weekend. The warning sign you see there is still up. It hasn't been taken down. That's a state-issued warning sign. This watershed is dense in livestock and poultry population. It's the most dense in Ohio. It's Ohio's largest inland lake. It's surrounded by 2 cities, St. Mary and Salina, on the northwest and northeast ends, and then it's also surrounded by homes. The entire lake is surrounded by vacation homes or permanent homes, and a lot of channels that allow boat access from those homes into the lake. It's the drinking water source for the city of Salina, population 10,000, and through Ohio EPA's monitoring and reporting, manure in runoff waters and storage issues for manure were identified in Ohio EPA's reports as one of the primary sources of nutrient inputs there. So in 2010, I think, we started working with Tetra Tech, that's Harry and I there, on what types of recommended actions will help protect and eventually restore the lake. So Tetra Tech was on the hook for providing a list of recommended actions, and they actually provided us a report in July of 2010 on those recommended actions. Down the lower right part of the screen is a kind of an example of what the watershed tributary system looks like. It's a channelized system absence of riparian corridor, absence of floodplain access. Over here on the left is one of the initial efforts to try to improve the situation in Grand Lake, when that had to do with installing treatment wetlands or a treatment train system on one of the tributaries going into Buckeye Lake, or excuse me, Grand Lake. So what were the recommended actions? In-lake recommended actions: lake treatment with alum. There were 2 demonstration projects with alum that happened for Grand Lake, and then 2 large-scale alum treatments have been done since then in the years after 2010. Dredging the sediments. Every year, more and more dredging is happening. I believe they have 2, sometimes 3 dredges in Grand Lake at any one time, and last year they dredged more than 400,000 cubic yards. Site-specific aeration. Homeowner associations around the lake have installed aeration systems in the channels to reduce odors and improve water quality in those channels because of the stagnant algae-laden waters in those. So that's been ongoing. In the watershed, wetland treatment trains. Let's see, we have 2 treatment trains already installed, both on Prairie Creek, which is about in the middle, and then we have one on Coldwater Creek that was just finished up this past fall. There are 4 others planned in this watershed. So that's an effort to pump water out of the tributaries and through the wetlands before getting to the lake. Education and outreach. You wouldn't believe how many different forums there are for people who are concerned with Grand Lake St. Mary's in this area, from government organizations to homeowners associations, to the college that's on the north side of the lake. There's a lot of stuff going on out there. And probably the biggest and most impressive efforts have gone into funding farm conservation planning and the installation of conservation practices. Like I said, we have a very dense livestock population. There is now this watershed is now a watershed in distress. It prohibits manure application on frozen or snow-covered ground. All livestock operations, except for the smallest, are required to have a comprehensive nutrient management plan. And once they did that, that made all these operations eligible for a special EQIP fund from USDA and RCS. And I'm not sure the exact number, but well over $10 million has been put into the watershed to implement best management practices, especially with regard to manure management. That's not to say that the streams have been fixed or channelization has been addressed or wetlands in the watershed has been addressed, but it's almost all been farmstead planning and additional storage and ability to manage manure. Another lake that we were asked to give an update on is Buckeye Lake. Buckeye Lake is about 30 miles east of Columbus. It's about a 3,000-acre lake. This lake, too, is surrounded by vacation homes. You can see this is the village of Buckeye Lake here, the Fairfield Beach community here, Millersport here, and then other communities, you know, vacation homes all around the lake, including homes on the dam itself. And that's been a different issue here, but that dam was deemed to be unsafe, and currently the lake, most recently the lake was drawn down and a new dam is being put up farther in from those homes. So a 3,000-acre lake was historically a large marsh wetland. It was impounded in the early 1800s to serve as a water supply for the Erie Canal. This lake has had harmful algal bloom warnings since 2012, and I mentioned a new dam is being installed. And one thing we do want to mention, there is a effective watershed group here called Buckeye Lake for Tomorrow, and an engaged soil and water conservation district. The Fairfield County Soil and Water Conservation District has done a lot of work in the watershed with area farmers. So on the bright side, the increased focus on the dam has provided potentially increased opportunity to address HAB issues here. Just an idea of what the watershed at Buckeye Lake looks like. The watershed here on my left is called the Buckeye Lake Reservoir Feeder. Historically, all those tributaries went on over to the North Fork of the Licking River, But in order to feed water, to provide water for the Erie Canal, this feeder creek was installed, a century or more ago, and now this watershed is probably the most important contributor of nutrients in the Buckeye Lake watershed itself. So a lot of the focus we have has been on the feeder creek. A lot more riparian areas on the south side, and less total volume. So again, we have our crews. There's Mr. Boney and Lewis again, and then we have our some high flow tributary monitoring. Let me tell you, that's not easy to plan for. In fact, we did a lot of tributary monitoring in this watershed to try to do a mass balance that Shannon will talk about later is necessary when you're developing plans. I don't know if every rainfall happened on the weekend during that period that year, but we were really happy to get at least a few high flow runoff events, but it's never enough. And you're always looking for more opportunities to collect more data, especially during high loading events. So what were the recommendations at Buckeye Lake? Continue the outreach and education, aggressively implement BMPs in the agriculture communities. Like I mentioned, we had a soil water conservation district that walked every tributary in the watershed, documenting tile outlets, documenting riparian areas. Other BMPs constructed, including wetland areas, was one recommendation. Stream bank to address stream bank erosion and otherwise reduce flow or runoff of nutrients. So those are a lot of agricultural practices, including drainage water management. In the lake, similar to Grand Lake St. Mary's, the recommendation from Tetra Tech was to treat phosphorus in the sediment, for instance, using alum. One thing that came out of this effort was there is a significant wildlife geese population at the lake, and there have been efforts to address that as well. And in addition, Buckeye Lake also has dredges on the lake as well, and dredging sediment to remove nutrient-laden material is important. So I'm wrapping up here. A lot of the reason we worked with Tetra Tech was we realized that collecting lake data was one thing, but using that lake data to try to address impairments was another. So it's not just the lake you need to know about. You need to know land use. You need to understand the tributary data, high flow data especially. Very important when you start into a localized lake, especially ones like Grand Lake and Buckeye Lake, where there's so many people who live on it or around it. You have to engage public officials. You need to engage water department officials, state park officials, and these regions, farming community is critical as far as land use. Lake associations can be a big help as well. So we are investing significant resources into sampling our lakes, and based on the data we collect and analyze, we are able to know now whether a lake is impaired as a public water supply or for recreation. And we list those impairments in the integrated report. But it's much more difficult to determine what are the fixes that are needed to restore use attainment. That's where the technical expertise provided by Tetra Tech through support of US EPA has been a big help to us in Ohio. Tetra Tech has now assisted us with 4 lakes, and we were able to put forth field resources necessary to understand as best as we could at Buckeye Lake and Grand Lake St. Mary's. You'll learn about some data gaps in the other 2 lakes here in a little bit. Most recently, at Lake Kaiser, Lake Alma, we didn't have the quality of robust data to develop a solid management recommendation. So as with any project or problem, the absence of data needed for planning and making decisions is a concern that needs to be addressed. So allocating sufficient resources is the challenge. We need to do lake water chemistry and biology, lake sediment sampling, bathymetry, inflow and outflow, mass balance, tributary sampling. We've evolved to a point now where it's time to determine what is the appropriate level of resources, staff, and budget that will be needed to begin developing planning documents that include a nutrient assessment, tributary inputs, outputs, and internal cycling beyond lake data that is increasingly abundant and available. This is indeed an evolution. Addressing HABs and lakes seems to have risen to the top lately, and we know that resources get reallocated by leadership in response to the issues of the day. But correcting problems in harmful algal blooms or nutrient-impaired lakes is a somewhat new expectation, especially as it relates to harmful algal blooms. So yes, of course, protecting and restoring lakes is important, just like protecting and restoring impaired rivers is important to our division. But the evolution isn't a smooth process, and it'll take a disciplined approach using all available resources, staff, funding, etc., as efficiently as possible. But we do think that by taking this approach that the lake management plan development process will eventually become commonplace, as it is for watershed protection and restoration plans. But the evolution continues. So the take from Ohio is we can't afford to throw darts in trying to address impairments in our inland lakes. It is critical to have the right information that will help efficiently direct measures. To hit the target, to protect and restore lakes, strategic management measures must be developed on an accumulation of the best data available and with full cooperation and assistance from lake stakeholders. We can't do this on our own with the staff and resources that we have. So once that's done, you need to get those measures that are identified effectively funded and implemented. Thank you very much, folks. That concludes my remarks. I know Harry and Shannon are up next to share their experiences, and if there's questions now or if we have time for questions, we can take them now or do them later at the end. Thank you very much.
Okay, thank you, Rick, for providing that excellent introduction. I think we all have now a better understanding of the evolution of Ohio's Inland Lakes program, and my compliments, my hats off to you all. Sounds like you're working very hard at addressing all the very complex issues. We're now going to take a few questions from the audience, and Kevin Kratt will be helping moderate the questions.
Okay, thanks, Ann. Yes, we do have a number of questions. I'm going to pick a few of those, and we'll see if we can get some of the others at the end. Rick, one of the first questions is, I think statewide, what criteria or guidelines are being used to determine when lakes are impaired by algae?
I believe it's the toxin data.
Okay, so based on the bacteria levels and guidelines, those are used to determine the impairments?
That's correct.
Okay. Then there's a few related to Grand Lake St. Mary's. One is just what the depth is, and then also a question about where the dredge material is disposed.
Okay. So what's the status of Grand Lake? A lot of resources have been put into out there, and a lot of effort. We do have 2 new USGS gauges on tributaries going into the lake at Chickasaw Creek and Coldwater. Along with that is composite chemistry sampling for daily loading. Obviously, every year runoff is different, rainfall and weather patterns are different, but latest report I heard from leadership is that we are trending down on the nutrient loads going into Grand Lake St. Mary's. That's not to say that they're at levels that are going to turn it directly around. Obviously, there's still no non-contact warning there, but there is some measured improvement with regard to nutrient management. Obviously, the farms in the watershed have had every opportunity to implement new storage systems. There's been manure removed from the watershed into other watersheds, so that's the good news there. What was the other part of that question? Oh, where's the dredge material go to?
Right, and the depth. Go ahead.
The dredge material is being pumped into what are called DRMZs, dredge material relocation zones, and those are on areas very close by the shores of the lakes, and at places where they can. Obviously, that's always a big issue. There has been talk about installing some new islands in the area if they need to.
Okay, great. Well, we do have some more questions, but I think in the interest of time, we'll keep moving, and we'll see if we can get to some of these others at the end. So back to you, Ann.
Thank you, Kevin. Thank you.
Okay, thank you, Kevin, for moderating the question and answer session. And now I'd like to introduce Dr. Harry Gibbons and Shannon Bradabo, who will discuss managing nutrients in lakes. And Harry will start off. Harry, the floor is yours.
Thank you, Ann, and thanks, Rick. That was great. So just to kind of review a take-home message of the Ohio Lakes Management Program development and evolution as it goes on is, well, like Rick said, most of the systems in Ohio, if not all of them, have been severely impacted by human activities. And a lot of the systems, both lakes and reservoirs within Ohio, have become over-enriched by nutrients from those activities in the watershed. And that some of them have become over-enriched to the point that cyanobacteria blooms are very common and sometimes toxic. And therefore, there's these following actions that Rick talked about and that we're going to talk about in a little more detail for a little bit here, have to be put in place. One, first, you need to have watershed management to control pollutants, specifically nutrients. And that control, if you have some water quality and excess production in your lakes, that control has to be accelerated over the typical levels, because the historic nutrient loading has resulted in overloading of the lakes and reservoirs relative to their ecological resiliency. In other words, their ability to handle the stresses, the environmental stresses that are induced by adding nutrients to the systems, and that results in poor water quality and algal blooms. Second, it may take tens to hundreds of years for a lake or reservoir to recover from the historical abuses of the watershed activities. So we need to understand that once a lake or reservoir system's resiliency has been exhausted, that you have to take very aggressive steps, not only in the watershed but in the lake, in order to maintain the beneficial uses and to protect the public health involved with those lakes. So what we're saying is both watershed and in-lake activities need to be based upon data. You need to understand and have a monitoring program that defines what the current conditions is and helps you identify what are the stressors that allows you to understand what are the best management approaches for reaching your water quality goals in the long term in a sustainable manner. To do that, as Rick said, you need a monitoring program to be in place and continue over time in order to provide the platform for an adaptive, sustainable management program that allows us to manage our lakes in a successful way. So with that, one thing we want to think about, and we'll just do some general discussion here for a bit, and then we'll get into some details. But lakes and reservoirs are just containers of water, but they're not simple. There's very complex elements. They're physical, chemical, biological. Everybody talks about that. But energy dynamics within the system also helps the interaction between the physical, chemical, and biological. Human activities, as we've discussed, a huge, huge factor. But all of these interact at the same time, so it's a complex situation. This is a perspective of the watershed. It makes you kind of feel good because, it's kind of nice. But what we need to really understand is, where's the balance? What's missing from this slide, which is classically used to educate folks in terms of a water cycle, is we're really underplaying the impact of human activity. Atmospheric sources, because of air pollution, are real. We don't really show the impact of roads, of development, urbanizations, rural development, and that sort of thing. We have some ag use here, but it really doesn't show how the water cycle, and therefore the impacts of the watershed on our aquatic resources, are really impacted. So we need to understand what is the, in order to understand the lake and reservoir, we need to understand what's flowing in, what's flowing out of the system, the morphology of the system, how much of what comes into the system is captured in the lake sediments, and how much of that can recycle through different mechanisms. So one of the key factors to remember here in terms of enabling nutrient recycling to occur is what is the residence time of the water, and what is the flushing rate, the effective flushing rate, and when does that occur, because that all leads to dynamic situations that enhances nutrient cycling and leads to water quality problems and excess algal growth. So first, we need to understand morphology. Is it a deep stratified lake that has different kind of mixing dynamics based on winds or not? Is it a shallow lake that has more polymetric, it mixes all the time, and therefore the nutrient availability is different? It also, that morphology governs whether or not dissolved oxygens are a very key factor in terms of the nutrient recycling ability and the physical mixing on top of that. So we have to understand these things in order to truly understand what is driving the system. That leads us to the nutrient cycling that we've been talking about. Basically primary productivity has classically requires macronutrients. We call them carbon, silicon, nitrogen, and phosphorus. Well, carbon, guess what? That's not a problem because we've over doubled our carbon concentration in the atmosphere in the last 80 years. So, and that's increasing. So that's a problem we got to address, but we're not going to address it specifically locally. That's a local and global issue. Silica has always been, and particularly as we started to understand our lakes and reservoirs, a limiting factor for certain groups of algae, like diatoms. But in shallow systems and systems where there's a disturbed watershed, silica isn't as limiting as it used to be 50 or 80 years ago. It's nitrogen and phosphorus that have been the excess nutrients put into the system through our watershed activities and the flushing rate that exists in the lakes and reservoir, and that's what we need to really look at. So here's a relatively simple, well, maybe a little bit more complex, look at nitrogen cycling. But what happens is nitrogen comes in from a variety of sources. It comes in from the watershed through inlets. It comes in from groundwater, which is watershed and beyond the watershed. It's more the water basin. It comes in from the atmosphere a lot. And let's not forget that atmospheric loading of nitrous oxides has increased dramatically in the last 50 years, strictly due to our automobile use. So we're adding to it. Then you have the physical chemical dynamics within the system, the sediment release of nitrogen into the organic water once it settles into the sediment. You have biotic activities such as that we need to understand. And so it's a very dynamic system. But one of the things that's really a driver once you get over enriched is this inner circle in the lake that shows the blue-green algae, the BG there, how the blue-greens, if there's enough phosphorus in the system, they can fix their own nitrogen from the atmospheric nitrogen. So now, instead of nitrogen and phosphorus being the key, once the system is pushed beyond its resiliency and you have blue-greens and you have blue-green blooms, they're predicting fixing their own nitrogen because of the excess amount of phosphorus. So with that, we need to understand that yes, nitrogen is important and we need to manage nitrogen, but we must also concentrate on phosphorus once the system has lost its resiliency and we have too many blue-greens in that system. And as Schindler et al. Pointed out in several publications, but the recent one in this last August, they conducted a study of numerous lake systems in Europe and America, and they found that the symptoms of eutrophications depends on reducing inputs of phosphorus. And so that's a key point that we want to talk about in terms of once you have a system that's out of balance, you need to look at phosphorus. Well, here's a general phosphorus cycle that's kind of neat, but again, it kind of underestimates the nutrient impact of the watershed on the phosphorus cycle. So let's get to a similar view of the phosphorus cycle that we talked about with the nitrogen cycle. Here we have, particularly if we want to pay attention to, is you have phosphorus coming into the system from the watershed. You have phosphorus coming in from dry bulk precipitation and wet precipitation. In some lakes where you have a lot of dust generated because of ag activities or other activities, this can be as high as 25%, but usually it's 5 to 10%, once in a while 15% from the atmospheric sources phosphorus comes in. But once it gets into the lake, notice that the arrow going out is almost always smaller than the arrow coming in from just the watershed alone, let alone atmosphere and groundwater. So that means that phosphorus is retained. That builds up the phosphorus in the sediments, and that recycles by many mechanisms. The most common that we've been talking about for decades has iron-bound phosphorus and the redox or lower oxygen levels and pH dependency of iron to hold that phosphorus. And if we lose our oxygen, the iron releases that phosphorus into the water column. But recently, when you over-enrich a system, we have a buildup of organic material that biogenic organics mineralize or release the organically bound phosphorus as soluble phosphorus into the water column. That means that biocycling in the water column itself, the algae can use that phosphorus and recycle it at a much faster rate. Also, don't forget, in lakes that have substantial amount of littoral area or shallow lakes where there's a lot of aquatic rooted plants, they enhance or magnify the nutrient internal recycling of phosphorus that's come in here. So that's a very important factor for us to understand. So looking into detail, if we look at the macrophytes here, there's several mechanisms that those macrophytes actually increase the nutrient phosphorus. One, the root and soil water face area below a very dense macrophyte bed may lose its oxygen. That causes the release of that iron-bound phosphorus into the water column. That's that sediment phosphorus arrow going out of there. The organisms that live amongst the plants, the insects, the fungus, the bacteria, and other paraphytic algae, they damage the aquatic plants, so there's a leak of phosphorus from the aquatic plants there. The aquatic plants themselves are a little bit leaky because they're sucking out phosphorus out of the sediments because they want to grow at a rate faster than they can utilize, and sometimes because of wind and mixing currents, that's an active leak into the water column. Then you have a physical abrasion of the plants themselves. They get broken. A boat goes by or a fish nibbles on them or things like that, and that causes breakage. And during that breakage, there's an active leak of phosphorus into the water column. All of that leads to the phytoplankton, which go, whoa, I've got more phosphorus. I can grow faster. And that leads us to this part of the phosphorus cycle, which shows how the phytoplankton really interact and magnify the phosphorus. So one of the things we want to talk about and understand is all the different mechanisms of phosphorus coming in here that are feeding these algae. And once we get to a point where the system now has been overloaded with phosphorus so that cyanobacteria now are dominating the diatoms and the other green algae and things like that, the good guys that feed into the food chain, we have the ability of the blue-greens to superuse that phosphorus, accelerate the use of it, so that the chlorophyll to phosphorus ratio that in natural systems and worldwide average is 0.3 to 1, chlorophyll to total phosphorus in the water column. But in a hypereutrophic or overproductive system that has been over-fertilized by watershed activities, that could go to 1 to 1 or 1.5 to 1. That means the chlorophyll is at a higher concentration than would be defined by strict balanced ecosystem in terms of phytoplankton phosphorus utilization to produce the biomass and the phytoplankton. Again, so phosphorus can be utilized at a greater rate by blue-greens, which create more blue-green algae, which contributes to our problem. So looking at this classical figure that NOMS produced back in the late 80s, early 90s, it shows on the left-hand side we have the transition from a natural system in which you have a stable watershed. Lake is oligotrophic, very low productivity, very good water quality, and it takes hundreds, thousands of years before that lake transitions to a eutrophic, overproductive or more productive system. In other words, it's that balance between flushing and retention of those nutrients and how long it takes before internal cycling and sedimentation and buildup become a driving force in the productivity. But in a reservoir, a man-made system, that whole translation from a very pure oligotrophic low productivity system to a very eutrophic system can take only tens to a few hundred years before we reach an over-enriched situation, a eutrophic to hyper-eutrophic, very over-enriched situation that has both sediment buildup, organic buildup, nutrient buildup, and that all translates to excess productivity. So that's one of the things we want to keep in mind. So how do we manage this whole thing? Well, first of all, we need to understand nutrient loading. What we're harping about here is let's look at it. 1 kilogram of phosphorus into a lake system that isn't flushed can grow up to 10,000 kilograms of algae. If that phosphorus doesn't leave the lake, if it goes into the sediments, it can potentially, under different situations, recycle up to 40 times. That means that 1 kilogram of phosphorus can produce 400,000 kilograms of algae. That's pea soup, and that's what we want to prevent. So hence, back to that earlier slide where I said retention or the flushing rate of lakes is very important to understand the impact of external loading in our systems. And so to continue, human activities can increase the background of nutrient loading, particularly phosphorus and nitrogen, 20 to 40 times. It could be 10 times for relatively controlled systems. So even at a 50% reduction through standard BMPs of your watershed loading to a lake or reservoir system, we're still talking about 10 to 20 times over background. That means it's going to age 10 to 20 times faster than if it was a grassland or forest background watershed. So what happens here is we have, if you go to a treatment train like Rick talked about, where we have multiple BMPs back to back in order to increase our efficiency of removal, and we remove 90% of what's generated from human activities, we're still 2 to 4 times higher than background. So once a system has been ecologically over-enriched, its resiliency is gone, just working with the watershed may not bring that lake back all by itself. So we may have to, in order to preserve our beneficial uses, look at what we have to do to sustain the lake itself. So what happens over time in a natural system over thousands of years is now compressed to just a few years, and we need to understand and reflect upon that. So one of the things I want to talk about here is we have to understand through a monitoring program of what's happening with the system. What is coming into the system, both surface water, groundwater, the relationship, and what's going out and how much is retained. So we need to understand that. In shallow systems, the retention versus the flushing rate becomes greatly enhanced. And so we need to understand that sometimes the resiliency of a shallow system isn't there like a deeper system. But we need to understand it and go for that. So some of the things that the bottom line that we want to keep in mind is the more intense of our land use activity, the more change we introduce to our freshwater environments. So what we need to understand here is, what is the relationship between pervious area and impervious area? That affects how fast it runs off, how much is stored, and that affects that water relationship or water balance. That affects how much nutrients are shoved into the system. What's the nature of the vegetation that's remaining, and how much does that store or impede the transfer of nutrients into our lake system? What is the nature of industrial, commercial, and residential activities in the watershed? And remember, ag has the potential to really fertilize our lake really fast, so we need to understand that. So what Betsy here told me in summary to watershed management is that once a lake's lost its resiliency and we have eutrophic conditions that have blue-greens that are producing things, the key is to manage our the watershed for phosphorus loading. Keep that down as small as we can. So it's that source of phosphorus, and because not only is it bringing in phosphorus directly into the lake, it's recharging what's already in the lake in the sediments that is recycling already. So that's a recharge thing that the watershed's doing. So that's a 1-2 punch that we need to understand. And that, anything that goes into the lake is just going to enhance the internal cycling once that system has lost its resiliency. So you always control the watershed, always try to turn it down, but sometimes you have to look at and go for in-lake activities, because without managing what's already there, all you're doing is trying to control the rate of recharge of what's already occurring. And in order to do your beneficial uses, you have to approach the problem from both. So what understanding through a management program and a monitoring program, what's going on is key to our understanding of where we're at. And what I always like to say, what is the quantity of phosphorus that's coming into the lake and from where, and what is the timing of that? Because the timing during the growth season when the sun's out, that leads to blooms, and that's one of the things we need to be aware of in order to move through. So this is especially true in the summertime, because if we have phosphorus becoming available to turn on the blue-greens during the growth season during the summer, then we have the blue-greens versus the good algae, and the food chain's not working as well, and we have excess blooms, and therefore our water quality goes down, and we have the potential for toxicity. So these are things to look at. So looking at these 5 lakes, if you look at the far right-hand column, and the numbers with the little 2 on the far right-hand side, that's the percent internal loading to these lakes on an annual basis. Klamath in Oregon, 59% of the total annual load of phosphorus to that lake is from internal sources. But the key here is 80% of the phosphorus during the growth season, during the summer months, is from internal sources. So watershed controls alone aren't going to turn around this lake. This is also a lake where phosphorus over-enrichment overrides the nitrogen, because what happens is, in the spring, nitrogen limitation's a big key factor in Upper Klamath, but ifanazomenon, which can fix nitrogen, is the dominant because it has too much phosphorus there. It comes on, it fixes nitrogen, that leads to microcystis production, which leads to microcystin, an algal toxin, and that creates a whole bunch of water problems. Let's go to Grand Lake St. Mary's, which on the bottom there, which Rick talked about. Here's an example of that recharge that I talked about. Internal loading is only 25% of the total annual load of phosphorus into that lake. But during the growth season, that internal phosphorus is 90% of the phosphorus availability to the algae. That's why during the summertime, they have those algal blooms. So we need to understand this. And in order to understand this, we need monitoring. So at this point, I'd like to turn it over to Shannon.
Thanks, Harry. As Harry has talked about, eutrophication and nutrient loading, and how it's important to understand the quantity and the timing of that nutrient loading in order to understand the best way to manage your lake. We are beginning to sound like a broken record, I think, going back and forth to the monitoring component, but it really is the most important tool that you have for not only assessing and understanding the lake water quality, but also is essential for moving forward with any management decision. As Rick pointed out earlier, you don't want to be throwing darts at a dartboard when it comes time to determine what is the best alternatives for managing your lake. You really need to have the background data to support those management decisions. And as Rick pointed out, and Harry, we've been working with the Ohio EPA now for several years, helping them beef up their monitoring program so that they can then take that data that they collect and use it successfully. So you may or may not be aware, there are several different types of monitoring that you can do in lakes and reservoirs, including water column profiling, usually done with a water quality sonde for things like temperature, pH, dissolved oxygen, and you usually do this throughout the water column at different depths. There's also continuous monitoring, which can provide a lot of beneficial information. Recently, we've been using these continuous loggers to give us more a finer scale information on temperature and dissolved oxygen in lakes to help us understand what's happening during stratification. You also do water quality grab sampling. This is the type of sampling used most often for collecting nutrient samples, chlorophyll samples, phytoplankton, and really is the backbone of your monitoring program. There's also sediment sampling, which can give you a lot of information in terms of nutrients and other constituents in your sediments. Bathymetric mapping is important, and aquatic plant mapping. As Harry alluded to, aquatic plants can play an important role in the phosphorus cycle, so it's really important to know what kind of plant community you have. Next slide, 45, please. So we generally recommend the following in terms of monitoring for your lake. Ideally you want to sample twice a month during that critical summer period, but there are always budget limitations. So if you can only do it once a month, that's okay too. You just need to be able to be consistent with your monitoring frequency. Usually you can get away with having one central site and at the deepest portion of your lake. This is pretty common in shallow lakes that are not as big as some of the ones that Rick showed us in Ohio. If you have a complicated system, of course you'll need more monitoring locations, especially if your lake has different bays or different arms. A lot of the reservoirs that we come across out here in the west are these long, elongated reservoirs formed by dams that have these three zones, the riverine zone, a transition zone, and then your lacustrine zone. So if you have this type of system, you want to make sure that you sample at least one station in each one of those zones. And most importantly, you want to make sure you're also sampling your inflows and your outflows, because knowing what's in your lake is not going to be useful unless you know what's coming into your lake and when it's coming into your lake. Slide 46, please. So there is a variety of parameters that you can sample for. I believe that the suite of parameters that are most important in terms of eutrophication and cyanobacteria issues are your basic nutrients, both total and dissolved phosphorus and nitrogen, as well as chlorophyll. Those should be determined near the surface. We usually do a half a meter below the surface. You can also do a meter below the surface and above the bottom. Even in a shallow lake, you want to make sure that you understand if there's a difference between surface and bottom concentrations. Phytoplankton and zooplankton samples can be very beneficial and provide you a lot of information, but unfortunately they're also fairly cost prohibitive. So maybe you only do once or twice a summer. Next slide, 47, please. So the most important part of a good monitoring program is the data QA/QC. It's really the only way to make sure that you're collecting quality data that's going to be useful. We typically recommend and practice collecting field replicates and duplicates, both in the water column profiling and for grab sampling. We also do field equipment blanks so that you'll be able to see whether any of your equipment is contaminating your samples. And you want to make sure that you review the lab data and their performance metrics. Are they meeting their lab blanks, spikes, and dupes? And that'll help you keep track of the lab performance. But most importantly, look at the data that you get and perform a reality check. Does the data make sense in the real world? We like to use chlorophyll to TP ratio. The worldwide average is 0.3, but it can range from 0.2 to 1 and as high as 1.5 if you have a system dominated by cyanobacteria. But if your chlorophyll to TP ratios are any higher than 1.5, you really want to take a step back and look to see, does your phosphorus data make sense with the amount of chlorophyll? Does your amount of chlorophyll make sense with your Secchi measurements? And there have been all kinds of relationships developed between these three parameters that you can use to help perform that reality check. It's really important so that you don't go into a management process and end up later realizing that your data may be a bit suspect. Slide 48, please. Once you take your monitoring program and you get all this great data and it's an ideal situation and you have, bi-monthly sampling, continuous flow data, what do you do with it? Well, what we like to do with it is create water and nutrient budgets. And this really helps you to determine and estimate both your external and internal loading, the changes in the lake, and most importantly, when that nutrient loads are occurring. How are they impacting the production of your lake? For water nutrient budgets, ideally you would want your flow information and your lake level information to be continuous. You know, you can install level loggers and flow monitors to give you that information. And it's best to have the 2-week time step for your nutrient budgets. These budgets, of course, can be developed from a less intensive data set, but you also often have to make some assumptions and realize that you may have large errors in your budget. Slide 49, please. So this is the basic water budget equation that I use when I'm creating these budgets. It's your change in storage of your lake is equal to all of your inflows minus your outflows, plus or minus groundwater, and precip minus evaporation. And usually you end up solving for the groundwater portion of this equation because that is the most difficult parameter to measure. You may have some information in terms of Grand Lake St. Mary's. We had a little information about the amount of groundwater leaving the lake, but in most cases that's the component of the equation that you won't have information on. Slide 50, please. So with your balanced water budget that you would have developed from that previous equation, you can then use this equation and your phosphorus concentrations that you've collected to come up with a phosphorus mass balance. Now, the mass balance is really important in that it helps you understand when and where the phosphorus is coming into your lake. So the equation is your change in lake mass of phosphorus is equal to all of your phosphorus coming in minus your phosphorus leaving the lake, usually through the outflow, and then minus the phosphorus lost via sedimentation. Slide 51, please. So rearranging that phosphorus mass balance equation allows you to determine your net internal loading, if it is occurring, and at what times it is occurring in your lake. So if you end up with a negative phosphorus sedimentation component on the left side of the equation, that indicates that the phosphorus leaving your lake and or the phosphorus change within your lake exceeds the external input, and so therefore there's net internal loading. For example, a lot of lakes here in the state of Washington, we have a lot of inflows that go dry during the summertime. So we know that there is no inflow of phosphorus coming in, but our lake phosphorus is continually increasing over the summertime. So we would use this equation to then calculate the mass of phosphorus being released within the lake during that time. Slide 52, please. So these budgets can be developed in an Excel spreadsheet. There's no fancy software or program needed. And you can then use the water and the phosphorus budget to then come up with a calibrated phosphorus model for your lake. And that model can be used to predict a lake response to various management alternatives, assuming a certain % reduction in TP loading. For instance, if you were to assume that an alum treatment would remove 80% of your internal loading, you can put that into your model, and the model will then tell you how your lake will respond in terms of surface phosphorus concentrations. This helps you make informed decisions on lake management. Next slide, please, 53. This is an example of a very complicated phosphorus budget that we did for Grand Lake St. Mary's. The first year, from 2010 to 2011. Most budgets that we deal with don't have this many inputs, but as you saw earlier, Grand Lake St. Mary's is a complicated system. You can see, though, that the summer 2010 internal loading accounted for 91%, or internal loading accounted for 91% of the summer load, but only 25% of the annual load. So it really allows you to pinpoint when your phosphorus is getting into your system. Next slide, please, 54. And then this is an example of the results of the calibrated mass balance model. So you see the predicted phosphorus concentrations in the lake in the pink line and the observed concentrations in the lake in the blue line. And we can get a pretty good fit with just these simple spreadsheet models, and they can be used as great tools for evaluating lake management alternatives. So with that, that was my brief talk about monitoring and mass balance and models. I'll turn it back over to Harry. Or I'll turn it over to Kevin for questions.
Yeah.
Yeah, this is Kevin. Yeah, we have a lot of great questions. Unfortunately, I don't think we're going to be able to get to them. Harry and Shannon, we're running a little behind schedule, so if we can try and pick up the pace for the second half. Let me just pick one of these on this topic. If you could maybe address this one quick, Harry. Our 38-acre lake has blooms in mid-October to early November. What factors could cause blooms in the fall instead of in the summer growing season?
That's where the morphology comes in, and understanding if it's a small lake that's relatively deep and then mixes in the fall, or it has a lot of plant growth that senesces in the fall and releases phosphorus. Either way, fall blooms are usually related to the third input would be that you get storm events coming in the fall. So one of those three things, external load coming in the fall with increased rainfall, mixing that occurs with a stratified system that's starting to de-stratify it, and you have internal cycling that's not available during the summer because of the strength of stratification, and or macrophyte senescence and release of nutrients. Those three factors could all lead to the fall blooms.
Okay, great. Thanks, Harry. Why don't you keep going? And again, we've only got about 45 minutes left, so let's try and get through the rest of the slides. Hopefully we'll still have time at the end for some more questions.
Yeah, I think we will. So this is Kaiser Lake, one of the lakes that Rick said that we looked at this last summer. It's located about 60 miles northwest of Columbus, Ohio, and it's managed by the Ohio Department of Natural Resources as part of the Kaiser Lake state park system. So the lake is a very shallow lake in that it's mean depth of 1.9 meters, so that's pretty shallow. It has a fairly large surface area in that it's 154 hectares, so it's pretty good. But it is a shallow, very productive lake. It has, for a reservoir, it was established in 1840, so it's been around for a long time. And one of its reasons for its resiliency until the last few decades has been that its residence time, its hydraulic residence time, is about half a year. So it flushes the water volume about twice during a year. That's a good flushing rate. Usually reservoirs have, that are not run-of-the-river type reservoirs, they tend to store the water longer, so their flushing rate decreases. So this is one of the reasons it's lasted as long as it has before it started to develop some water quality problems. But let's talk about those water quality issues a little bit here. So its ratio of water area to watershed is about 15 times, but 70% of the watershed, as shown here in this figure, is mainly agricultural. Now, one of the saving graces is that surrounding the reservoir immediately there is a kind of a buffer zone of wetlands and forest land that helps buffer the impact of that intense watershed activity. But nevertheless, it is a disturbed watershed that is starting to show the impacts over time of the watershed land uses on the lake itself in terms of the excess algae and the macrophyte density that occurs in the shallow lake. So when we start to look at the water quality of this system, we start to understand that it's not horrendous in terms of its water quality, but it's starting to show it has excess chlorophyll and it has excess phosphorus, and its Secchi disk is typical of a eutrophic, very productive system. As mentioned earlier, this gets to the point of looking at our QA, QC, like Shannon mentioned and Rick talked about, in terms of the quantity of data you have and the quality of data. You need to understand, do we have validated and is it telling us the true story? And so that's something that we've looked at the data both historically and currently and had some questions and felt that we need some more data in order to truly understand what is driving the system. And so with the occurrence of toxic blooms that are occurring here, that becomes a very important factor to understand. What's causing these toxic blooms? Is it just strictly the watershed loading? Is it a combination of watershed and internal, or is it internal because of the timing? And then recharging that internal from over time because of the watershed. So in order to understand that and to limit the potential for toxic blooms that are occurring in this water contact lake, we need to understand. So if you look at sources of phosphorus in the watershed, if you just look at as if the watershed was all forested, we'd have a loading into the lake about 330 kilograms per year. But with the advent of having 70% of the watershed ag, now our estimated loading from the watershed is 2,300 kilograms per year. So that's 7 times more phosphorus coming into the system than would be natural. So that's why over time the lake has developed into an overproductive system. So that's one thing that we know, but we still need some more monitoring to understand. So again, I mentioned the fact that we have some forest around the area, we have some wetlands around the area, so there is some external watershed buffering and resiliency that's helping to absorb things, but nevertheless, excess phosphorus has got to the system, and so we have a hypereutrophic lake in terms of its water quality conditions. We have a lake morphometry that's very shallow. So even though the Secchi disk is only half a meter, you only have 2 meters of basic depth, so with any kind of little wind action, phytoplankton can be lifted into the water column. You also have a shallow system that's going to encourage aquatic plant growth, which is good when it's in balance, but when it gets excess because of excess nutrients, then you have excess recycling that feeds the algae as well as the macrophytes, and then you get too much density that impacts the aquatic habitat when the density of the plants becomes too dense and you lose oxygen and other things. So all these things have to be taken into consideration and understand what is the exact mechanism of internal cycling within the lake. Is it iron redox reductions with wind suspension and or mineralization of organics, or is it biological activity by the fish that are present in the lake stirring up things, or a combination of all of these things together? Again, that's why Shannon talked about we need to construct a mass balance in order to understand what's going on in this system. So what we're really looking at here is how do we define that? So what we need is a monitoring program that's fairly intense to start with, and then you can scale back and collect long-term data, but you need to start. And as Shannon talked in general, we need to understand what's in the lake. So we take samples. This is a fairly small system, so 2 samples, one at half meter and one at half meter above the bottom. So that's in the photic zone and below the photic zone, so we get an idea of the nutrient differential between those 2 zones, as well as the biological activity that goes on. So we have to sample that. Also, we want to understand what's coming into the lake. In other words, what's flowing in. So it's not only just taking, when we're out there taking a sample of the lake, we take a sample of inflow. We take special samples during at least 6 storm events to understand how the storm event and the different intensities of storms affect the loading from the watershed into the lake, and how much resiliency is left in those natural wetlands and vegetative riparian zones that still exist in some of the inlets right before it approaches the lake itself. So we have to really have an idea of what's coming in so we can produce a water budget and define how much water is coming in, when, and how much nutrients that's carrying into the system. So data loggers, like Shannon mentioned, are really fairly inexpensive and good tools to use to get lake levels, to get levels in the stream. Then you can measure the flows and relate instantaneously, even to events you don't sample with the change in the height of the stream. You can relate to how much water is coming into the system and help you do that water budget that then helps you do the mass balance, which is really important. I mentioned in biology, we need to sample the aquatic plants. You need to sample the phytoplankton to understand who's there and what's there, what the density of both the aquatic plants in the shallow system and the phytoplankton are, and who's present, what kind of species, what is the community structure, and how that changes over time in order for us to understand what's happening in the lake and what are the things that we need to do in order to help us control it. Once you have this monitoring data in place, then you can sit down and look at how do we analyze the data. And I know Shannon and I keep harping on, you need to have some basic budgets. You need to know how much water's going into the lake, how much is leaving the lake, how long it's retained in the lake. You need to know with that how much nutrient loading is coming into the system, because it's the loading that matters, and how much is flushed from the system through that nutrient balance, how much is retained, and then how much is coming back as recycled from the sediments and other biological activities. So with that, then you can look at, well, what would be the impact of reducing our external loading? What would be the impact of reducing our internal loading? What combination thereof would actually maximize the cost-effective approach to do things? And how do we control our water quality, enhance our water quality, and limit the occurrence of those toxic algal blooms that are causing direct impact on its use? So these are things you need to consider. Shannon, you want to talk about Alma?
Thanks, Terry. Lake Alma is another lake that Ohio EPA asked us to look at and help provide them with some management recommendations, as Rick mentioned earlier. Lake Alma is located about 60 miles southwest of Columbus, and it's within the Lake Alma State Park. This park is a very popular site for summer recreation, which includes boating, fishing, swimming, hiking, and camping. And this recreation is what is driving Ohio EPA to take a look at this lake. Next slide, please. Lake Alma is a very small lake. It's only about 64 acres in size, and it has a mean depth of 2.5 meters and a maximum depth of 5 meters. So not necessarily a classic shallow lake, but not a really deep lake either. The lake does stratify during the summer, which plays an important role, we think, in the nutrient dynamics. The lake has been historically and periodically used as a water supply for the city of Wellston, Ohio, although it's not their main water supply. So it's another reason why the Ohio EPA is very concerned about this lake. Slide 69, please. So the Lake Alma is part of the larger Raccoon Creek watershed, and the region that the lake is located in has historically used for mining. And as a result of that mining legacy, there are 2 impoundments upstream of the lake in the eastern part of the watershed. And in the mid-1990s, there was an extreme heavy rainfall event which caused those 2 impoundments to be breached and resulted in a large sediment load to the lake. And we think that this large sediment load is continuing to contribute to some internal nutrient loading within the lake. Slide 70, please. So as you can see, the Lake Alma watershed is actually very small, only 455 acres. The lake itself makes up 13% of the watershed by the area, so a very small watershed compared to the lake. The watershed is mostly forested with just a small amount of ag land consisting of crop and pasture land to the eastern part of the watershed. We believe that there is one small minor inflow to the lake. Unfortunately, this time we don't know much about the inflow, and we feel by talking with the folks at the Ohio Department of Natural Resources that the lake is predominantly fed by precipitation and groundwater. So again, without knowing much about the hydrology of the system, we can't really determine where the nutrient loads may be coming from that are contributing to their water quality issues. Slide 71, please. So as was the case for Kaiser Lake, when Ohio EPA asked us to look at Lake Alma, we quickly realized that there was a very limited amount of data available for us to use. There were two sampling dates in 1980, and then Ohio EPA went out and collected samples twice in 2015. So that's all the data we have to work with to write a lake management plan, which is pretty much impossible. Or not impossible, but again, it would go back to the throwing darts on the dartboard. So if you look at this data, the 2015 Secchi and chlorophyll data suggests that the lake currently is in a meso to eutrophic state, so fairly productive. The 1980 data suggests that it also was probably a mesotrophic system in the 80s. In contrast, though, the 2015 phosphorus data paints a different picture, suggesting that the lake has very low nutrients, as the surface water samples were below the detection limit. And the detection limit for the Ohio EPA is 10 micrograms per liter. They usually choose half of that, 5, for their datum assessment values. So again, we take a step back, looked at the data quality, and came to the conclusion that maybe the phosphorus numbers in 2015 were an underestimate of the actual loading. Slide 72, please. We do know that Lake Alma has experienced and is currently experiencing harmful algal blooms, and probably due to an excess of nutrients. In 2010, there were 2 probable human illnesses reported by the Department of Health, and a microcystin concentration of 275 micrograms per liter. All the recent toxicity data has been at or below the detection limit, but there have been algal scums present. So we know that there's a problem, but overall it's difficult to assess the condition of Lake Alma because we have such a very small data set, and we really don't know anything about the hydrology of the lake. Slide 73, please. Given the small amount of information we had, we did have some land use data, so we used the land use data to try and predict and estimate the possible external loading to the lake. Unsurprisingly, the model estimated that the cropland is the form of land use that contributes the largest external load of phosphorus. But without knowing exactly the hydrology of that inflow, we don't actually know if that load gets to the lake or when it gets to the lake. And we really can't base any management decisions on this simple land use model. The watershed nutrient loading can be estimated more precisely if we had that available water quality and flow data. Slide 74, please. So what can we say about the nutrients in Lake Alma based on the data we have? There looks like there's a difference between surface and bottom samples, and that there are probably internal phosphorus mechanisms existing in the lake. So given those low DO concentrations, the fact that it's a really small watershed, and the lack of a major inflow, we can assume that there is internal loading contributing to the cyanobacteria. But again, without more monitoring data and without a mass balance model, we can't actually say with any accuracy or any we can't determine what that load is. Next slide, please, 75. So unfortunately, we weren't able to give Ohio EPA specific recommendations for management except to conduct at least 1 year of intensive monitoring, very similar to Kaiser Lake. Monitor at the deep site for nutrients, temperature, DO, chlorophyll, but also to continue their testing for cyanotoxins, especially since this is a high recreated lake. Next slide, please. And again, the most important part was to get a better picture of the understanding of that tributary to Lake Alma. Does it contribute water? Does it contribute loading? Do we need to focus on watershed management activities, or should we focus more on in-lake management activities? So again, we proposed this to the Ohio EPA, and we said we can't develop a lake management plan quite yet without the necessary data. Next slide, please. So hopefully, when the data is collected, then they can use that to determine the current trophic state of the lake, determine the water and phosphorus budget, which then leads to estimates of external and internal loading, and then they can understand and make an informed decision on what would be the best alternative method for, or best management alternative for Lake Alma. Slide 78, please. And of course, as with any restoration activity, you want to include long-term monitoring in your implementation. So these are the long-term monitoring things that we recommended to Ohio. You know, once they understand their system a little bit better, maybe they can cut back on the number of sampling and the number of parameters that they use. I really think Lake Alma is one of those special cases where if we just had a little bit more information, then you can make a really good management decision and help the lake, restore the lake, and help curb those harmful algal blooms. And with that, I will hand it back over to Harry, who's going to briefly talk about different in-lake management alternatives, some that we considered both for Kaiser and for Alma, and hopefully with a little bit more data, Ohio EPA can use some of these alternatives. You got it, Harry?
Hope you're not muted, Harry.
I was for a second. So the whole point being that understanding through monitoring what is the condition of the lakes and reservoirs, what is the overall stressors, where are they coming from, then you can look at what kind of activities, both in the watershed and lake, that you can do. But as Shannon said, here's a brief review of some of the alternatives that have been considered and been shown to be successful under certain circumstances in lake. So we'll start off with dredging. Dredging's, you know, you're getting rid of that reservoir that has built up of nutrients over time and organic matter and all sorts of things. So it's a good approach. It's fairly expensive if you don't have a very inexpensive disposal site, such as Grand Lake St. Mary's has the ability to put the soil back on, the dredge back onto the ag lands, which is, you know, nearby, so it doesn't have to ship, so it holds the cost down. But that's one of the things. The other thing to keep in mind when you're dredging is the completeness of the aerial dredging. In other words, like you mow your lawn, you have to go back and forth and overlap. Because if you don't, that material that you left is going to slough, and so the same characteristics that exist on the surface of the sediment before you start dredging now still exist, even though you removed a whole bunch of sediment, because it'll slough over the deeper part of the sediment. So you've got to make sure that the dredging is carried out fairly well. Well, in order to do that, you need to characterize what is the nature of the sediment. How deep do we have to dredge in order to remove our target compound, phosphorus or nitrogen or both, or organic material? And what areas do we need to dredge? You don't necessarily have to dredge everything all the time. You can target those areas that are actually the highlights in terms of bringing about internal cycling, or the drivers in terms of excess primary productivity. So you need to understand what the sediments are. And again, the other point is when you've exposed new sediments, there's going to be a new sediment-water interaction, a new equilibrium that's going to establish, and that results in release of nitrogen and phosphorus, particularly phosphorus. So sometimes in some systems, you need to, when you dredge, you need to inactivate that sediment so that you don't have a 2-year period of dramatic algal blooms from the release of that newly exposed sediment. Another alternative is hypolumnetic withdrawal. So in a deep stratified system, you remove the bottom waters out of the lake, essentially flush it out of the lake. Well, in order to maintain the lake level, you need to make sure you have a low nutrient source that you're putting in, otherwise you'll draw the lake down. You also have to remove about 15 times the water volume out of that deep layer in order to keep up with the internal cycling that occurs. So a couple offsets there. So you have to have a source of low nutrient water to offset what you're taking out. You're also, the other disadvantage here is you're shoving your problem downstream. So that may not be approved of, but it is something to consider, particularly in smaller systems that are reactive that way. Another approach is dilution. If you have a source of fresh water available that's of low nutrients, you can flush that system and dilute the water that's in the lake because of internal cycling and external loading in the long time, but the internal cycling that's building up and releasing. If you flush the lake at 2 to 15% of the water volume per day, you can keep that productivity at bay. And it's a two-pronged advantage. One, you're decreasing the phosphorus in the lake by flushing it out. If you have a lower phosphorus concentration of your dilution water than what's in the lake column, so you're flushing it out. The second is if you increase the flushing rate, because blue-greens don't grow that fast compared to other algae, you're giving other algae a chance to outcompete the blue-greens, and so maybe you won't get those surface scums and the toxic blooms. So there's something to be said about dilution. Aeration and circulation. The key here is what is controlling the phosphorus. Is it redox or lack of oxygen and iron-bound phosphorus being released and solubilized under anoxic conditions, lack of oxygen? If that's the case and we have adequate iron that in the sediment and the water column that's 15-to-1 in both, then you can go with a circulation thing to try to do it. The other factor with circulation in a deeper lake is if you circulate fast enough, you can starve the algae of light. So the rule of thumb is you circulate fast enough so that the water is mixed so that only 1 out of 3 days an algae particle is going to be exposed to light, and for 2 days it's in the deeper dark zone. So you have to circulate the whole lake at a fast enough rate, and you have to be deep enough to have light, to limit it by light. So you've got two things going. One, is this iron controlled? If it's not iron controlled, you've got to go with light, and or can you do both, light limit and iron control by providing oxygen through the mixing. So those are the key things to aeration and circulation. Hypolymnetic aeration is a form of aeration, but you're just maintaining a deeper stratified layer with oxygen in order to, again, enhance that iron-bound phosphorus capability to hold that phosphorus into the sediments by raising the dissolved oxygen and raising the redox potential so that it remains as ferric iron, which holds the phosphorus and doesn't reduce to ferrous iron, which then releases the phosphorus. But again, your sediment phosphorus ratio and your water column ratio has to be 15-to-1 iron to phosphorus to be effective. And you also have to put enough oxygen in the system, whether you're using pure oxygen or mixed oxygen or air, compressed air, to raise the dissolved oxygen right off the bottom to 4 milligrams per liter. And this can be done. And the picture here is Lake Stevens, which was one of the deeper hypolymnetic systems that was ever built and operated for 20 years. Another way to control your phosphorus in your water quality and algal problems is the phosphorus inactivation. There's 4 basic strategies. 1, prevent it from coming in from the watershed. That's called intercept it before it gets there. 2, strip it out of the water column periodically so it's not in the water column so the algae can't grow. That's really good for smaller systems. Or a maintenance treatment where you're treating it after the load comes in from the watershed and you're making that biologically inactivated by adding a flocculant to remove the phosphorus out of the column. Or the approach that's been shown to be really effective, neutralize that phosphorus reservoir in the nutrients in the sediments, by adding alum, for instance, or aluminum to bind that phosphorus and hold it in the sediment so it never gets back up into the water column. So the mechanisms are basically 4 metal ions, the aluminum, calcium, iron, and lanthanum. And the mechanism is the metal is the active ingredient. That's what grabs the phosphorus. So you've got to expose that metal when it's hungry or in the right charge, hydrated rate to grab that phosphorus, transport it out of the system or into the sediments, and then hold it there so it's no longer biologically active. One key factor we've talked about, iron and redox and anaerobic conditions where it releases phosphorus. So if you have a situation, a stratified situation or a mixed situation in which you have low iron or anoxia, the iron isn't going to be a metal that you want to add to the system to control the phosphorus because you don't have enough of it, or you have conditions that the iron isn't going to keep that phosphorus in the sediment. pH is dependent upon calcium, so you have to have a higher pH system, and most sediments have a pH that the calcium phosphorus eventually erodes. So that hasn't proven to be a great utilitarian. Aluminum has been proven several times to be highly effective and very good. Lanthanum is assumed to have that, but the cost as a rare earth and the data that we have on long-term hasn't necessarily shown yet. And in Europe recently, the papers that were presented at NOMS and Banff just a few weeks ago, they talked about they did a lanthanum treatment, but then they used iron or aluminum addition in order to take the lanthanum and deliver it to the sediment. So there's still some studies that have to be done before we can just openly recommend that. So the most successful has been aluminum sulfite, alum, adding that aluminum in there to bind with that phosphorus and remove it. There are several lakes that you have what's called maintenance treatments over time. Long Lake, Kitsap County, 1980, 91, and 2007 to inhibit and stop those toxic blue-greens from occurring. Green Lake in Seattle, which is a very highly urbanized system. The whole north end of Seattle drains into this system. It's named green because it was green naturally before the city was developed, and it's got 6 to 8 meters of sediment that's high in phosphorus reserve. So dredging is not a cost-effective approach to the system. So a periodic alum treatment to keep those HABs, the occurrences, limited. And Grand Lake St. Mary's 2011, 2012, that's what these pictures are, an alum treatment to demonstrate that, yes, we can buy up this phosphorus once we get the watershed in control as much as we can. We can preserve this water supply by tying up that phosphorus. So in summary, internal loading in shallow lakes may be more important in terms of the external loading during the summer or during particular times of year. So we have to understand that. In shallow systems, even modest flux lakes from the flux out of the sediment or loading from the sediment can be extremely important. So we have to understand how that leads to potential HABs. And standard watershed BMPs are only going to address part of the increase of phosphorus due to our land use. So we have to be very aggressive and comprehensive and understand where are the sources so that we have an effective application of our watershed BMPs to control the current thing. But what about the historic? That's already led to a decline in the resiliency of our lake. Then we need to look at inactivating that phosphorus or reducing that phosphorus or somehow managing that internal loading of phosphorus so it doesn't produce the blue-greens. I'm high on phosphorus inactivation only because it's been one of the most proven effective ways of going about it to date. Still looking for new ways, but that seems to be an effective way. But we always must keep in mind that you have to turn off that faucet, which is the watershed. You have to manage the watershed, and you have to manage the lake in concert in order to achieve your water quality goals. So with that, I think we're almost there. So I think Anne's going to talk a little bit and summarize, and then we'll go to questions.
Okay, thank you, Harry and Shannon, for presenting the lake management planning topics and the case studies, as well as the last section on some of the in-lake BMPs, as well as watershed practices that are needed. We're going to have time for some of the questions that have been asked, a number of excellent questions, but first I have a few final announcements. We will do some questions, but if all of your questions are not asked today or answered, you'd like to contact our speakers, you can find their contact information on this slide. So please do feel free to contact them. And I want to let you know that we are planning our next webcast, and we hope you'll visit our website in the coming weeks as we post additional details on the topic, speakers, and how to register. So please check back with us at www.epa.gov/Watershed Academy for more details about the next webcast. And also, don't forget to download the certificate. This certificate can be downloaded from EPA's server through the link on this slide. Please type this link into your browser to download the PDF document, and you can personalize this certificate with the names of everyone that is watching from your location. And now we're going to have time for questions for our speakers. Kevin, I think we've got a number of questions. Take it away.
Okay, thanks, Ann. Yeah, I've just picked a few of the questions from all three, sessions of the presentation. I guess first one is probably for you, Harry. Why is alum treatment typically implemented for lake sediment rather than for the sediment being transported while it's still in the feeder channels or the tributaries?
Again, it comes to what kind of monitoring data you have and understanding what is the most cost-effective. The interception, which is the technique that's being discussed, that was asked about, intercepting that phosphorus in the sediment before it gets into the lake system, that's what we call interception. And that's part of what Rick talked about in terms of having a treatment train where you use alum injection to remove the phosphorus, and then you deal with that sludge in a variety of ways. But once the resiliency of a lake has been exhausted, the internal cycling has to be addressed. And therefore, even though if you stop what's coming in, it may take a long time for it to recover. Like Grand Lake St. Mary's, we estimated from our mass balance it was going to be 30 to 40 years before that lake recovered, and it's a drinking water source, so it's important to understand what options are available. Lake Okeechobee, we estimated, depending on your assumptions and models, that the recovery of the watershed would lead to recovery in Lake Okeechobee, which is the water supply for a third of the state of Florida. It would take between 40 and 400 to 800 years before the lake recovers. So they're trying to do the watershed first and get a handle on whether or not they have to do the in-lake things. So to make a simple answer to the question, inactivation of the sediment buys a period of time, whether it be 5 up to 20 years has been observed that you inactivate the sediment, you are going to be free of the algal blooms for a period of time, unless your excess coming in from the external loading is such that it's real flashy, and that's what's driving your blooms. If that's the case, you want to do the interception first. But if it's already the internal cycling from the sediments, you may have to do both, or you need to concentrate like Green Lake. You're concentrating because of the cost effectiveness of it. $3 billion to fix the watershed and intercept the phosphorus in the watershed before it gets there, or $500,000 to $1 million every 10 years to treat the sediments in the lake. So that's why.
Okay, thank you. Next one, this might be for you, Shannon. There were a couple of questions about, like in the tables that you showed of doing the mass balance budget. How do you, estimate the actual internal load when you're putting those together?
So when we set up the mass balance, we first do the water budget, and we set that up on a 2-week time step. And so then that leads to the phosphorus mass, the nutrient budget being set up on a 2-week time step. And then that will give you a number for the phosphorus sedimentation component of that equation for each 2-week time step. And if that number is negative, then that indicates that you're having an increase of phosphorus within the lake, and that can't be explained by the external load. So then you can add up, ignoring the negative signs, add up all those internal, all those numbers, and that gives you an estimate of your net internal load for that time period, for that year, say, if you were doing a 2-week time step on a yearly basis. Does that answer the question?
Yeah, I think that does. Just kind of by subtraction or whatever is how you get the estimate of the internal load by difference.
the great thing about phosphorus is that it's all about the conservation of mass. You have a mass of phosphorus in the lake, a mass of phosphorus coming into the lake, and a mass of phosphorus leaving the lake. And so if you have the right data, you can run the pretty simple equations.
Okay, great. Thanks, Shannon. Rick, maybe this one's for you, but what coordination is happening within the ditch and tile systems in these watersheds? Is Ohio developing drainage improvement projects to try and address nutrient and flow reductions?
Most definitely. We're very aware that tile contribution of phosphorus is an important source of phosphorus coming from especially the agricultural cropland regions. Both in our non-point source management plan, the state of Ohio's nutrient strategy, and the types of grants we've applied for from the Great Lakes Restoration Initiative all include flow reduction and drainage water management considerations. The idea is, yeah, you have a certain concentration of phosphorus in tile drainage waters or surface runoff, but half of the equation of the load is definitely flow, and if you can reduce the flow reduction during especially high runoff events, you can reduce the overall loading. Yeah, then there would be some more low flow or base flow where the streams can assimilate, or there could be some nutrient spiraling in the stream. So definitely drainage water management is a key component of our strategy moving forward in all of our agricultural watersheds in Ohio, especially the Lake Erie watershed.
Okay, great. Thanks, Rick. This might be for you again, Harry. Do you know of any success stories where dredging has permanently solved eutrophication issues, i.e. eliminated harmful algal blooms and excessive weeds?
The word permanent is tricky because there's a reason why the dredging was an effective way of going about. So a 50-year life cycle, depending on the watershed, is probably the life cycle you plan for in a dredging operation, because the dredging's needed because of watershed activities in the first place. So there are examples of where dredging has lasted for a number of years, but remember that if you don't address the watershed, you're going to be back to dredging again. So, and the second part, like I said, when you dredge, an example would be what we learned from Liberty Lake in the 70s when we dredged a portion of that lake, that we applied an alum treatment to that dredged area, which really then resulted in 20 years of benefit. So that phosphorus inactivation after a dredging is something to always think about when you characterize your sediment. But as far as dredging is concerned, it will give you a long-term, depending upon that external loading. So again, you have to have that mass balance to understand where the stresses are and what's going on, because that watershed has to be managed all the time. That's why the problem occurred in the first place.
Okay, and you kind of addressed this next one a little bit, but if you can speak to this a little bit more, how long does an alum treatment last? I mean, you said 20 years, but that can depend on the lake and the situation, right?
Yeah, an alum treatment's going to be depending upon whether it's a maintenance treatment that you're doing annually or periodically in a smaller system, or whether you're doing an inactivation treatment that can last from 5 to 20 years. So it depends, again, on the data you have and how fast the sediments are recharged from the watershed. So at Green Lake, we're seeing 8 to 12 years in between a very large watershed to lake ratio builds up the nutrients to the point that we have to inactivate again to prevent the blooms. Long Lake, it's varied between 8 years to 20 years. Several lakes in the Midwest, like Darlow Lake was a 20-year thing. So it really depends on the relationship between how much is annual coming in from the watershed versus internal, and when the timing of the internal occurs that gives you the longevity.
Okay, I think we have time for a few more here. Another one, I'm not sure this did apply for these lakes, but if you know this in general, Harry, do any of the lakes discussed today have zebra mussel infestations, and if so, how does that taken into account for lake management?
I'm going to refer to, well, first of all, if there's zebra mussel in those lakes, I'll refer to Rick, but relative to management of the lake, the zebra mussel is going to change a lot of dynamics in the system, and you may see a temporal improvement and then a decrease over time because the excess nutrients lead to that. So zebra mussels are a mixed bag, but they're gonna only lead to long-term larger problems. But Rick, are zebra mussels reported in Grand Lake or Buckeye? I don't think they're in Kaiser or yet.
No, not to my knowledge.
Yeah.
Okay. I think one of your slides, Harry, I think there was a kind of a reference that 1 kilogram of phosphorus can create 10,000 kilograms of algae or something along those lines, and we had a few questions about the source of that statistic or how you calculate that.
That came from Hutchinson's work in the 50s and some of the work he did over time, and that's wet weight of algae, and the potential for 40 times recycling doesn't mean that phosphorus getting in there is going to recycle 40 times. That's the upper potential that Hutchinson put together and with his dissertation essentially way back when published on. So that's historic stuff that's been verified over time.
Okay, great. Let's see here. Maybe just a couple more for either Rick or Harry. We had a couple questions early on about other sources in Grand Lake St. Mary's, such as septic systems around the shoreline and geese. So if either you want to speak a little bit to the, magnitude of those or ways to address those. I guess, Harry, just in general, what are some thoughts on controlling loads from septics and geese?
Okay, geese are very important. For instance, Lake Ballinger, we did the mass balance, and we found that geese and ducks, waterfowl, were contributing 25% of the load to the lake. At Lake Stevens, we found that it was a very significant portion of 45 to 50% of the annual load of phosphorus. And remember, it only takes 3 geese or mallard ducks to equal a human in terms of phosphorus production. So they're very active, and at making a deposit in the lake water 28 times a day, they contribute phosphorus greatly. So management of geese is very important. Waterfowl and geese is very important. There's several ways to do that. You can do it with, just to harass them via radio control boats, planes, or dogs, all of which addling the eggs so that they don't become resident. They're very important factors to consider and manage. Septic tanks, again, understanding the nature of your soils and the interflow and groundwater relationships is important. Again, you can track phosphorus coming from septic tanks through a variety of ways. I've done it with both P32 and uranium, actually, back in the day when detergents had a lot of phosphorus. The uranium is a contaminant that you can track. So there's different ways to understand it, but just doing some shallow half barrels to seepage meters to understand the septic input is an easy way to do it, or piezometers in the system.
With regard to the lakes that we talked about here today, both Grand Lake St. Mary's and Buckeye Lake are now completely sewered around the lakes. They weren't historically. I would like to put a date on that for you, but it's been over a decade at least on each of those lakes that they've been sewered. Like was mentioned in Kaiser Lake, there is one community of about 70 homes on septic systems. that's a question that we would need to look into if as we look toward management strategies. And we've also applied for and received a grant for, or provided a grant for harassment using dogs at Buckeye Lake and another beach somewhere in Ohio. The name escapes me. That's all.
Okay, great. I think we're all done. Thank you again for everyone's questions, and if we didn't get to yours, feel free to reach out to the speakers directly.
Okay, thanks, Kevin. And the speakers, at this time, I'd like to conclude today's webcast. Thank you all for joining us, and of course, thanks to our amazing speakers. And that ends our webcast for today. Thank you again.